Brilliant. You changed the crocodile.
Yes, I try to give a new crocodile per lesson.
I see.
If anybody has interesting crocodile pictures that I can use as backgrounds, you're more than welcome to send them to me. I'll use them in future efforts.
Funny. So I think we can start. So welcome to this second lesson on dark matter. We have again Leonid with us, teaching us something about dark matter. Today we are starting with beyond the WIMP solution for the dark matter problem. So please, Leonid, go ahead.
Okay, thank you, Luca. So hi everyone, welcome back. So yesterday we did in our first lesson, we did some general introduction to dark matter, a little bit of sort of the cheat sheet of what we'll need to know about early universe cosmology, and we started going, listing different types of 2-to-2 interactions that could set the relic abundance of dark matter in the early universe. And what we're going to be doing today, and we focused on what's typically called the WIMP, although I hope I've convinced you that this is not really a weakly interacting massive particle, but something much more general. And having built and developed all sorts of tools and methods and tricks in order to solve for the WIMP, what we're going to do is move beyond the WIMP today. And I'm not going to be able to go over all of the different mechanisms that we've mentioned or that exist in the literature, but I will tell you which ones we're going to solve together today. Some you guys will be solving also in the TA session, the tutorial session on Thursday, and just sort of today is beyond WIMP. So our outline, we're going to start by, oops, sorry, my screen jumped around. So the first thing that we're going to start with today is we're going to work through the case of forbidden channels. Then we're going to do another 2-to-2 process that we drew, which are called co-annihilations. And then a couple of other 2-to-2 processes will be discussed in the tutorial session on Thursday, and we're going to move beyond 2-to-2. We're going to talk about 3-to-2 interactions, or more generally N-to-2, and this is going to be a strongly interacting massive particle, or in short, a Simp. And the last topic that I hope we manage to finish today is we're also going to be talking about cannibals. Okay, so that's our rough plan for today's lesson, and let's start with the first one. Let's start with forbidden dark matter. Forbidden channels. Okay. So forbidden channels, until now, when we considered our WIMP, I remind you that I'll always be denoting dark matter as some particle chi. And so we were looking at 2-to-2 annihilations yesterday, where I had 2 chi's that annihilated into 2 other bath particles. And yesterday we solved this in general for the case of the WIMP, but I want to consider this process now in a different kinematical regime. So let's look at the case where the sum of the incoming masses is smaller than the sum of the outgoing masses. That's sort of as a most general case. And of course, for the simple 2-to-2, what that means is that the mass of chi is smaller than the mass of phi. Now, of course, at 0 temperature, this process is forbidden, right? So at 0 temperature, this process is forbidden. It's just kinematically not allowed to happen. But as we discussed, the early universe is a thermal environment. So the early universe is a thermal environment. And so what that means is that this process can happen if the chi particles, the dark matter particles, are living off of sort of the Boltzmann tail of the distribution. Okay? So this process can happen, and we're going to see exactly how this comes about, of course. So it can happen by living off of the Boltzmann tail of the distributions. Okay, so let's see how this happens. Okay, so let's write down the Boltzmann equation. Okay. Now remind you, when I'm considering, I drew a diagram like this, and actually there are 2 processes that can be happening, right? Usually we have time going this way, right? So this would be the annihilation process. But I also have to write down, and indeed our Boltzmann equation takes care also of the term where I'm producing particles in this direction, right? So both of these processes are happening, and our Boltzmann equation takes into account both of them. So let's write out what this looks like over here. So our Boltzmann equation, so remind you, we start off with dn dt, the change in time of our number density of dark matter particles, plus 3nh. So part of the change of time is coming from the fact that the universe is expanding. That's why we have this second term, which accommodates the expansion via the dependence on the Hubble parameter. And now let's write out these two contributions, the annihilation piece and the production piece, okay? So for the annihilation to happen, okay, which is removing particles, so I have a minus. I have, and you know what, let's make sure we put over here, since we have two particles, I'll denote that by n chi, right? So we're looking at the number density equation for chi. So I have minus n chi squared times the thermally average cross-section of chi goes to phi, right? That's my annihilation term. And from the opposite direction, the production, I have a plus sign, and now I have to have two phi particles meet each other, so it's n phi squared, and these particles are in equilibrium, so I'll add a little equilibrium there, and now I have the thermally average cross-section of the inverse process, phi goes to chi. Okay, so I take into account both of these pieces, and the trick that we're going to do is to use, again, detailed balance. So here's our trick. Use detailed balance. To understand, you see this cross-section over here, which is a cross-section of the annihilation term, it's happening in this weird kinematic regime where the mass of the incoming particle is smaller than the outgoing particle. Okay, so that's why there's a little bit of extra care here, and the way that we're going to be able to understand what's going on is by using detailed balance. So let's do this. Okay, now remind you that in detailed balance, what it tells us is that when we're in equilibrium, this right-hand side of the Boltzmann equation should vanish. Both of these processes are rapidly happening, and so in equilibrium, I don't lose any phi's or produce any phi's. And so if I take right-hand side over here equals 0, what that tells me is that in equilibrium, minus n chi squared equilibrium times sigma v of this chi goes to phi, plus n phi squared equilibrium sigma v of the not forbidden direction, the production direction, this should equal 0. And so now let's solve for the cross-section that we're interested in. This sigma v chi goes to phi, that forbidden channel. Okay, so this is the forbidden direction. And what we get is that this equals n phi equilibrium over n chi equilibrium squared times the thermally average cross-section for phi goes to chi. And the reason that it's nice that we were able to write it this way is because this cross-section over here, right, this one is just an ordinary cross-section in which it's not a forbidden channel, it's the direction which can happen very easily. And so, you can kind of think of this cross-section, this is sort of the ordinary 2-to-2 cross-section, which I can think of parameterizing as some alpha effective squared over m chi squared. Okay, it's just an ordinary 2-to-2 cross-section. And so plugging this back into our Boltzmann equation, what we have is dn dt of chi plus 3h n chi. This now equals minus, so let me pull out, you see I'm writing everything now in terms of this unsuppressed cross-section, the ordinary cross-section for the non-forbidden case, times n chi squared e to the minus 2. You know what, actually, sorry, before we do this, apologies, let's just do one more explicit step, okay? Oops. Okay, let's just, let's take a look at what this ratio of, let me mark it off over here. Let's take a look at what happens to this ratio of number densities, okay? So from in equilibrium, if these two particles, a number density in equilibrium of a particle that's non-relativistic, if you remember we saw yesterday, it's exponentially suppressed. Okay, so these number densities each have an exponential suppression, And so importantly, what we get in terms of scaling over here is that this ratio has, so for the phi particle, there's going to be some e to the minus m phi over temperature, and for the chi particle, e to the minus m chi over temperature. And so the ratio of these two number densities squared is going to give me an exponent that's sensitive to that mass difference. Okay, so this is going to go like e to the minus 2 because it's squared, m phi minus m chi over temperature. Okay, so that's going to be the factor that we have over here. And so if I put all of this together, what you see is that this, okay, so let me move this down here. You see that this cross section over here, the forbidden cross section, roughly scales like e to the minus 2 delta m over t times this ordinary unsuppressed 2 to 2 cross section. Okay, so the forbidden thermally average cross section is exponentially suppressed compared to the not forbidden one. And so now let's take all of this and plug this back into our Boltzmann equation. So as we said, our Boltzmann equation is dn dt plus 3n chi times h. And this equals, so let me pull out this thermally average cross section of the unsuppressed direction. Phi phi goes to chi chi. And now what we see, again, looking back at our Boltzmann equation over here, so I had n chi squared e to the minus 2 delta m over t minus n phi equilibrium squared. Okay, so all I did is take this, this squiggly cross section that we had up here, that's what we've put together over here. Okay, and we found that it looks like this. And so I've pulled out the common unsuppressed cross section and just inserted the exponential suppression that we got. And so now, given this Boltzmann equation, let's work out when freeze-out happens. So here's my freeze-out condition. So freeze-out happens when the rate for the process we're interested in, chi chi to phi phi, is of order Hubble. So let's write out what this rate is. So the rate is, of course, proportional to, so it's proportional to two pieces. It's proportional always to the number density of the particles that I need to meet. So always think of it as if I'm a dark matter particle, who do I need to meet in order for this annihilation to occur? So that will give me 1 power of n chi, because I have to meet one dark matter particle. And then times the strength of the interaction, this thermally average cross-section, which is what we denoted here in this squiggly pink. That's our forbidden cross-section, right? So that is e to the minus 2 delta m over t. And now times the ordinary cross-section, which I said we're going to denote as some alpha squared over m chi squared. Okay? And this should be of order Hubble, and Hubble is t squared over m Planck. Or I remind you that we often use this variable x, which is mass over temperature. So mass of chi over temperature. So I can write this as x at the time of freeze-out, because that's when we're interested in, squared over m chi squared times m Planck. Okay, so this is our freeze-out condition. Okay, and so what you see is that this looks kind of almost identical to the case of a WIMP. Okay, the only difference is this exponential piece that's sitting over here. Okay, so this is the only difference from the WIMP equation that we derived yesterday. And so now we just, as we did yesterday, we simply, we solved this equation. So I want to write down either the general cross-section for this case, or alternatively, the mass as a function of the coupling. These are equivalent. And what we find over here, if I just take out what is m chi, you find that m chi starts off looking very similar to the case of the WIMP, which is alpha effective, the coupling strength that's appearing there, times the square root of t equality and m Planck. And if that was all, this would be the WIMP. But we have this extra exponential over here, and that's what's coming in next. We have an exponent of minus, I'll call it delta x, where delta x is just this, okay, delta x is this, delta x is the delta m over t. Okay? And so what we found right now, so let's just, let's underline this. So this is the result that we found now for the forbidden case. What you see is that this mass Let me actually move, oops, just 1 second. Let me remove this from here. And just write that down here. Okay, so delta x was delta m over t. And what you see is that we found something that is naturally much lighter than the weak scale. This is exponentially smaller than the results for the WIMP. Okay, so for same alpha, for same coupling, I get a mass of dark matter that's predicted to be exponentially smaller than if it was an ordinary 2-to-2 annihilation. Okay, so this is exponentially smaller than the WIMP case. Let's write that out. Exponentially smaller masses than sort of the WIMP-like case. Okay? And as we'll be able, we'll also be discussing hopefully tomorrow, what this basically predicts for us. So you see, in general, this shows me, depending on the size of alpha, I'll have some size of m. I get exponentially lighter dark matter masses than the case of the WIMP. So this typically points you to light dark matter. Okay, light dark matter being something that's, let's say, beneath the weak scale, and typically even beneath the GV scale. But importantly, it's difficult to go beyond sort of a KV for a variety of reasons that we'll hopefully be discussing tomorrow. So this typically points you to masses of dark matter that are above KV and above. Okay. Now, importantly, the picture that we had in our mind yesterday that we developed for what freeze-out physically looks like, it's just identical over here. So I do want to stress this. So just note the following two things. First is that the freeze-out picture is exactly the same as what we saw for ordinary freeze-out. If I look at number density over entropy as a function of x or of temperature, then this picture that we drew yesterday where dark matter freezes out, the picture is qualitatively identical over here. Okay? It's just that the mass scale that we're pointed to is exponentially smaller. And the second thing that I want to also note is that, likewise, if you were to ask yourself, at what temperature is this freezing out? What is the value of xf? You still get that xf is of order 20, just like we had before. Okay? So that's all I wanted to say about forbidden. And now that I think of it, I think I forgot to give you guys references for forbidden dark matter. So let me just scroll back up here. Sorry about that. And write out the two references for this. So this was an idea that was first put out in a paper by Grist and Seckel in 1991. It's a paper that's called Three Exceptions. And it was sort of recently revived in a more recent paper by Ruderman and Dagnolo in a PRL that was number 1505.07107. Okay, so these are references in case you guys want to look into it a little bit more. Okay, so those are forbidden channels. And now unless there are questions on this, the plan is now to move on to talking about co-annihilations, a different 2-to-2 mechanism. So here we are, co-annihilations. Okay. And again, this is still within the 2-to-2 zoo, within the family of 2-to-2 annihilations. And this is something that also can be found, an idea that's in this Grist and Seckel paper from 1991. So let's look at the following case. Until now, we sort of, we assumed we had some particle chi and it had these 2-to-2 interactions, but we didn't really consider interactions thinking of this particle as if it was one of some tower of states, of some dark sector with, let's say, n particles that all interact with each other, and that all of these interactions can contribute to the dark matter abundance. Okay, so let's look at the following situation. Imagine that I have a whole tower of particles. Okay, I'm going to call them psi I. So let's say psi I annihilates with psi j and goes to 2 phi's. Okay, so imagine that I have some tower or some spectrum of I don't know, big N dark states. Okay, that's how many dark states I have. And the lightest one is the dark matter. So, oops, lightest one is our dark matter. And imagine that we have, so there are rapid processes that are interchanging interchanging sort of the identity of chi-i's are talking to chi-j's, and things are sort of shifting around. So this is the case we're looking at over here, is that when the whole tower, in principle, and it could be just some subgroup, but that there's more than one particle, the whole tower can, in principle, can participate at the time of freeze-out. Okay. And so here's my sort of tower of particles. Okay, I have Here's my chi1 will be my, oops, let's make that a more readable label. So chi1 is my lightest state, and then I have some chi-i's up to some chi-n. Okay, and so all of these particles are participating at the time of freeze-out, and the assumption is that at some point, but they also have interactions. They sort of rapidly exchange energy between themselves, and eventually these are all sort of going to decay down to the lightest state. Okay, and this is in general, this whole system would be described by n-coupled Boltzmann equations. Okay, so now just here's a little trick that we're going to use, or sort of the setup. We're going to assume that there's rapid exchange. Chi-i's speak very quickly with chi-j's. Okay, and so this is what this is going to do, is it's going to set the chemical potential of particle I to equal that of particle j. And this could be happening, either because some chi-j is decaying to some particle phi, through some interaction, and chi-i, or maybe these particles are scattering off of some other abundant particle. Okay. So what this means is that I can think of this whole tower as being in chemical equilibrium with itself, okay? And the importance of this is that something that's happening to any of the chi's is going to affect the relic abundance of dark matter. Okay, so the tower is in chemical equilibrium with itself, And so what this tells us is that we can approximate the ratio of the number densities of particle I and particle j as their equilibrium densities, and this removes n-1 of those equations. Okay, and so what we can end up doing, this is the bottom line to take away from this short discussion, is that the bottom line is that what we can do is just consider one equation for, let me write down the total number density sitting in all of these chi's. Okay, so I'll call it n, and that is going to be the sum over all of the ni densities, so it's the total number density. Okay, and the reason that we care about the total number density is because, as I said, eventually everything is sort of going to cascade down and sit in the dark matter. So whatever abundance I have for the total tower is what I'm going to observe in dark matter. And so we can go ahead and write down the Boltzmann equation for this total number density. Okay, and so what you find is that dn dt plus 3nh has the following form. There's a minus, and something I'm going to call sigma v effective, we'll define it in a moment, times n squared minus n equilibrium squared, where this effective cross-section, okay, so what you would really do is write down the Boltzmann equation for each of these particles, okay, and each one has its own sigma ij of the interactions that are happening for it, but I can sort of sum all of those together and reach this this form, where this effective cross-section that I find sitting over here is the sum over all the ij particles, and it's ni equilibrium times nj equilibrium over n equilibrium squared, times each individual sigma ijv, where the sigma ijv is that cross-section for the ij particle annihilating into phi's. And so in this way, we're able to capture the entire behavior of this tower with some effective cross-section that's taking into account each of the individual components that is annihilating away. But let's take a closer look at what we see over here. So if I look at this equation, okay, so I have here, right, this is the equation that we reach for. This is our Boltzmann equation, right? And it's It has this effective cross-section sitting over here. And you see that the equation is identical to the equation that we had for the WIMP, right? It's just that it has some effective cross-section that's sitting in over there, okay? So this is identical. Oops, let's do this in a different color. Identical to the WIMP. Otherwise, in other words, other than this effective cross-section. And so just like for the case of the WIMP, we knew what the size of that cross-section had to be, right? And we can use that same condition for the cross-section just over here. Instead of requiring that a 2 to 2 sigma v equals 1 over T equality in Planck, which we found yesterday, now require it for sigma effective. Okay, so we just use the same condition, except now it's this sigma v effective. This is what we require to be of order what we found yesterday, 1 over T equality m Planck. Okay? And that's because the equation is identical, so I know what size the cross-section has to be, and now I can interpret it in terms of this sigma effective. Okay, and so importantly, what you see already from this form of the sigma effective is that it's completely arbitrary at this point, before I specify a model, which particle is the one that's playing the most important role, okay? So, you know, typically you would think for the WIMP, definitely the particle that's annihilating away is the dark matter particle. In this case, it could be that the dominant contribution to this effective cross-section is coming from some other particle that's not the dark matter particle at all. Maybe it's the dark matter particle that's annihilating away with somebody higher in the tower, and it might even be that it's annihilations of two particles that are neither of them dark matter, that's controlling the dark matter relic abundance. Okay? So let's just write that out. So what we're finding over here is that this sum, and thus this effective cross-section, need not be controlled or dominated by the lightest particle. Okay? And in particular, and this is a point that I think for, at least certainly for me as a student, it took a while to really sort of comprehend this, that literally the dark matter relic abundance could be determined by interactions that are not involving the dark matter particle itself. Okay? So in particular, I want to stress this, the abundance could be set by interactions that are entirely of completely other particles in the tower. Okay, so that's something that's really important. That, you know, sort of said another way, is that the abundance can be determined and can be independent of an actual annihilation of the dark matter particle. Okay. And this co-annihilation situation is something that it even happens in supersymmetry. So I know we're used to, if those of you who've ever learned supersymmetry, and you know, very often if somebody was teaching a course on dark matter, certainly a decade ago, WIMPs and supersymmetry would be pretty much the whole course. I just want to point out that supersymmetry, even though it's usually linked to WIMPs, even it itself has co-annihilations in it. So that's this is actually a pretty generic situation, even in supersymmetry, and certainly something that that in principle, just as we see, just something that can be happening. Okay, and of course this has important implications for phenomenology of dark matter, because if you think about, you know, trying to measure, trying to detect dark matter in some way, this tells you that it's not necessarily the case that the interactions of dark matter and annihilations or scattering of dark matter themselves are linked directly in size to the process that's setting the relic abundance. Okay, so that's an important takeaway. Okay, so that was the case of co-annihilations. There are another couple of 2-to-2 mechanisms that Miguel is going to hopefully be solving with you guys in the tutorial session on Thursday. What I'd like to do now is move even further beyond the WIMP, move past 2 to 2. And now we're planning to talk about 3 to 2 annihilations. And in particular, we're going to see this is called Simps. Okay. And if you're interested in references for reading more about this, so this is an idea that I put out a few years back. So it's from myself, Kuflik, Wolanski, Wacker, in a PRL with archive number 1402.5143. Interestingly, this is an idea that we came up with and worked through on the beach. So in case you're ever wondering, excellent physics can be had in good times and good locations. Okay, so what is a simp? So let's assume, sort of generally, that, imagine I have some dark matter particle, and it's some lightest, it's a lightest state in some dark sector. Okay, well, and let me call it a secluded dark sector. Okay, you're going to see in a moment what I mean by this. So some secluded dark sector. Okay. So let me forget for a second. Until now, we talked about how dark matter was interacting with other stuff. Let me for a second ask the question, what if what's important is not how dark matter interacts with other things, but how it interacts with itself? Okay? What if what's important isn't how dark matter interacts with other things, but rather itself? Okay? So in this case, the first process you might think of going to is looking at a 2 to 2 process, right? But if I look at 2 to 2 interactions, chi-chi goes to chi-chi, then that is not a process that changes the number of chi particles. It's just a self-scattering process. So self-scatterings, self-interactions, self-scatterings don't change the number density. Okay? And the first process of self-interactions that does change the number density are 3 to 2 annihilations. Okay, so the first process that does are 3 to 2 annihilations, where I take 3 dark matter particles and I shoot out 2 on the other side. Okay, so chi, chi, chi goes to chi, chi. Okay? So let's ask ourselves, if this process is determining the relic abundance, what's the Boltzmann equation, what's the Freezeout condition, and what's the cross-section, or the relative size of mass and the relationship between mass and coupling that's needed for this to give us the right amount of dark matter? Okay, so let's use the estimating tools that we've developed so far. Let's use the estimating tools that we've developed. Okay. So here we go. I'll write down the Boltzmann equation, and we're actually not really going to be working from the whole Boltzmann equation. But if you write down the Boltzmann equation for the system, it looks like dn dt plus 3hn. I'll write it in the following way. There's some minus. I'm going to call it sigma v squared of the 3 to 2 cross section. We're going to explain everything in a moment. And then I have 3 dark matter particles that are meeting, so I have an n chi cubed. And the back reaction turns out you can write down as n chi squared, n chi equilibrium. Okay, and this is of course all the number density of chi's. Okay, let's just take a look at the Freezeout condition. Okay, this is sort of the Boltzmann equation in case needed. But let's look at our Freezeout condition. So Freezeout happens when the rate of the 3 to 2 annihilations, right, the rate of whatever process we're interested in, is of order Hubble, of order the expansion of the universe. And let's walk through what this rate is for 3 to 2 annihilations piece by piece. So the rate for 3 to 2 annihilations, so remember we have these 2 factors. I have the factor that takes into account who do I need, if I'm a dark matter particle, who do I need to meet in order for the process to occur, and then times my thermally average cross-section. So for all the cases we've done so far, when it was a 2 to 2 process, if I'm a dark matter particle, I have to meet one more dark matter particle. or one more particle, and what was that identity of the particle depended on the process. But over here, if I'm a dark matter particle, because it's a 3-to-2 annihilation, I have to meet 2 other dark matter particles. So I'm going to be proportional, the rate is going to be proportional to n chi squared. Okay, so this is, that's the first piece. It's n chi squared because I have to meet, if I am a dark matter particle, I have to meet 2 more. Okay? That's the first piece. And the second piece is the thermally average cross-section of this 3-to-2 process. So I'm going to denote that as sigma v squared of 3-to-2. And this is just a notation that I use that's really counting for just the name I'm giving for that whole collision term, which has the matrix element squared for this process, integrated over the phase space, etc., as we've spelled out last lecture. Okay? So this is just the 3-to-2, like the 3-to-2 cross-section. The reason that we, by the way, choose to write over here, and this is really just notation. The reason that it's sitting here is this velocity squared is related to sort of the fact that we kind of just think of this as if there's some cross-section and then you have a flux of 2 particles coming in. So from the flux, you sort of have flux is number density times velocity, and we have it squared. Okay, but this whole thing is just a stand-in notation. Stand-in. Oops, let me write that more clearly. This is just a stand-in notation for the collision term. Okay, but this is our freeze-out condition. The rate for 3-to-2 is proportional to number density of dark matter squared times this thermally averaged 3-to-2 cross-section. And of course, what we need is for this to be of order Hubble. Now let's just take a moment to understand how can we parameterize this this kind of weird object, this 3-to-2 cross-section. Okay, so this 3-to-2 cross-section, sigma v squared of 3-to-2. Now, 2-to-2 cross-sections are obviously much more familiar. We all know that they look roughly like, in terms that they scale with 1 over m squared. 5-point interactions, or like diagrams that have 5 legs total, are probably a little bit less familiar. Let me parameterize this in the following way. So I'm going to parameterize it as some coupling alpha effective cubed. And we'll explain later in the toy model why I'm taking cubed, but again, it's just a way to parameterize the cross-section, to sort of parameterize our ignorance until we write down a model. And then in terms of dimensions, this is actually dimensions mass to the -5. So I'm going to divide by m chi to the 5th. Okay? We're going to see a little bit later some nice ways how one can understand what's the dimension of this thermally average cross-section. Okay, but in terms of dimension, this is actually correct. And you can also, if I take a look at what my rate equation that we just wrote down here is saying, that also makes sense because, gamma of 3-to-2, which should be of order Hubble, that's a rate. It has the mass dimension 1. Okay, so another way to sort of make sure that this is all making sense, right, is that my rate, the dimension of this is mass to the power 1, right? And then dimension of n is 3, right? Let me just write this down as numbers instead of mass to the power. Okay, so I know that I have to reach dimension 1. Number density is dimension cubed, so n squared is dimension 6. And so this already tells you that this sigma v squared 3-to-2 has to be dimension -5. Okay, just so that everything else is making sense. Okay, so that's just sort of a sanity check that this is indeed a good way to parameterize the cross-section. Okay, so we have our freeze-out. We've written out our rate. Now it needs to be of order Hubble, and so let's see what we get. So the next thing we're going to do is take the number density of chi at freeze-out, and I remind you guys that everything here, this whole equation is at freeze-out, right? So let me remove that from here. So yesterday we saw that we can take the number density at freeze-out from I'll call it our redshift to the time of matter radiation equality. So it's a T equality trick. Okay, so this is what we derived yesterday. We redshifted from freeze-out until T equality. A T equality, given measured quantities, we know how to express things. And what we found was that n chi at freezeout, I remind you it's scaled like t equality m chi squared over x freezeout cubed. Okay, this was the result that we obtained yesterday. And so let's plug this into, let me call this over here, into this equation star. Okay, so let's plug this into this equation. Oh, sorry. Well, it's this. Oops. Now we want to demand that all of this, of course, is of order Hubble. Okay. So let's plug this in and see what we get. So what we get. So I have n chi freezeout squared. So I'm just going to start off by squaring everything that's here. So I have t equality squared, m chi to the 4th over x freezeout to the 6th. Next, I have my thermally averaged cross-section, which we said we're going to be denoting by alpha effective cubed over mass of chi to the 5th. And we require that this is of order Hubble. And so we require that this is of order t squared over m Planck. And again, moving to the x parameter, what I get is m chi squared over x freezeout squared m Planck. Okay, so this is our requirement from freezeout. And now let's just cancel out. So, collect over here. We have, let's see, on the left-hand side, we have 1 over m. And on the right-hand side, we have m squared. So I end up with an m cubed. So if I want to write down, so I'm going to have m goes like a third root of lots of other stuff. And let's just write out what that comes out to be. What we find is that m chi is of order alpha effective times t equality squared m Planck to the power of 1/3. Where I'm being sloppy with my order 1s and my x freezeouts, okay, because they're not going to qualitatively change. But this is a very important result. This is what we find now for the Simp. Okay, this is what we find for this 3-to-2 process. That there's a very different relationship between the mass of the particle and the coupling that we use to parameterize the cross-section. For the WIMP, we found that it went like mass goes like alpha times just square root t equality m Planck. And now we have mass goes like alpha with a generalized geometric mean between these two scales, t equality squared and m Planck. And if you plug in proper numbers, what you find is that this goes like alpha effective times 100 MeV. But I remind you the equivalent for the WIMP was m went like alpha times 30 TeV. Okay? So this is this equation is, if I compare and contrast to the WIMP, so we said this is sort of this generalized geometric mean. And so now, if we look at this equation, now it happens to be the case that if I take alpha to be order 1, to be of order of strong coupling, then 100 MeV emerges. The strong scale emerges. Okay? So over here, what we get is that if alpha effective is of order 1, now the strong scale emerges. Okay? And this is, again, on equal footing with, for the WIMP case, where if I put in a weak coupling, the weak scale emerges. Now I put in a strong coupling, the strong scale emerges. So this is what we called a strongly interacting massive particle, strongly sort of, let's put in self-interacting massive particle, or instead of a WIMP, we called it a Simp. So this is what's called in the literature the Simp miracle. Okay? And importantly, what this means is that if this 3-to-2 process is what's responsible for dark matter, we get much lighter dark matter masses, okay, than what we've been considering before, and also very different interactions. Okay? So here we get strong self-annihilations of dark matter. And the dark matter is typically between the MeV and the GeV scale. Yeah, Luca, there are questions?
A curiosity. So even this method doesn't depend on the initial conditions, as we discussed yesterday, isn't it?
So let me get through one more thing, well, two more things, and then we'll discuss how I just cheated you. Not exactly, there's a hidden assumption, so I can already say it. There's a hidden assumption in what we've done, which was that these particles were in thermal contact with the standard model, right?
Okay.
So we're exactly gonna get to that and make sure that the setup is sort of kosher. Okay.
Okay. Thank you.
Great question.
There's another question. This large coupling is not constrained by any measurement?
So again, something that we're going to talk about more tomorrow. So what this coupling is telling you, and again, there's a range. It doesn't have to be an order 1 coupling. It could be smaller. It could be up to 4 pi. And again, also I stress this is an effective parameterization of a cross-section, which in a particular theory, you would go ahead and compute it, and there might be other order 1s that would come and enhance it. But in general, this points to having sort of a large self-interaction. And it's true that you would think that if I have a theory with large 3-to-2 interactions, I would also have large 2-to-2 self-scatterings. And those are indeed, in principle, there are constraints that come from dynamics and dark matter halos, and we'll be talking about those a little bit tomorrow. And those are definitely, over here, something that, definitely one of the types of constraints that you need to think of. As we'll mention tomorrow, these self-interactions are something that there's a little bit of, there's some questions in the literature about whether there's room for actually, maybe there are hints that we actually should have some amount of strong self-interactions. And so this definitely points you to saying, on the one hand, you can be okay with bounds, but maybe even be contributing in a way that would be addressing some questions in structure formation. But yeah, there is, of course, anytime you write down a theory like this, a theory of any of the types that we've been talking about, you have to work through what are all of the sets of constraints that could potentially be relevant, and having a strong self-interaction is definitely something that you have to keep your eyes out for. But it's not, it's allowed, but it is a constraint.
Okay, thank you.
Okay, so having derived what we get for what is the relationship between mass and coupling that we have for the case of a simp, I just do want to point out over here that even in this case, you could ask yourself, okay, I mean, obviously to get this number, I've assumed something about X freeze out, about the temperature at which it's freezing out. And I just want to show you that even in this case of 3-to-2, remember we said that X freeze out is always going to be roughly 20 because I'm always just logarithmically sensitive. Let's just work that out explicitly over here, okay, because that is indeed the case here as well. So let's just write this out. So just note that X freeze out is still ballpark of 20. Okay, so let's just look at this the following way. Freeze out when we're non-relativistic, okay? And we're going to see that it's a self-consistent assumption. So freeze out when you're non-relativistic. So, you know, the number density of dark matter goes like, we wrote it out yesterday. It's m times temperature to the power of 3/2 e to the minus m over t. Okay, so we had an n squared in our equation that we needed. N squared goes like mt cubed e to the minus 2 m over t. Okay, now we had our freeze-out condition was n chi squared times this sigma v squared 3-to-2. Okay, so this is going to go like mt cubed e to the minus 2 m over t times alpha effective cubed over m chi to the 5th. And this had to be of order Hubble, which was m chi squared over x freeze out squared m Planck. Okay, and so you see, just like in all the cases when we're looking at 2-to-2, what's important is that x freeze out is still sitting here in the exponent. Okay, so this is minus 2. You know, this is exponent of minus 2 x freeze out. For the WIMP, it was minus 1 x freeze out. But what's important is that it's still sitting in the exponent, and so eventually we always end up with x freeze out that's just logarithmically dependent. So here it's minus half log of the mass times, logarithmically dependent on, here it comes out to be on x freeze out, the mass over m Planck. But importantly, you plug in the numbers, and this is still just always logarithmically sensitive on the parameters, still of order 20. So dark matter, even in this case, is freezing out. So these simps are freezing out when they're non-relativistic at temperatures that are a factor of 20 beneath their mass, just like was the case for the other 2-to-2 processes that we've considered. Okay, so that's it's just a note on freeze-out temperatures. Okay, so we've worked out the 3 to 2 case, and I'd like us to briefly work out the n to 2, a more general case of n to 2 annihilations. So more generally, we can look at some n to 2 as a general case. Okay, so, and it could be, for instance, maybe you can't have 3 to 2 annihilations because maybe your dark matter is a fermion, in which case, so maybe actually that's worth writing out. So, if dark matter is a fermion, then you can't have 3 to 2 annihilations. So 3 to 2 can only happen for scalar particles, or maybe there's some Z2 symmetry that's preventing these types of processes. So it's still interesting to ask what happens for higher point interactions, again, just considering these self-annihilations of dark matter. Okay, so let's work this out. So here's my n to 2 process. I now have many n particles, 1, 2, until n, that are annihilating into some other particles, and these are all self-interactions. Okay. And so in this case, I'm going to need, in a similar way, to parameterize some even weirder object, some thermally averaged n to 2 cross-section. Okay, so I'm going to write it in the following form. I'll call it sigma v to the n minus 1 of this n to 2 process. Again, just a stand-in for the collision term, or for the matrix element squared with the averaging, etc. And let me just define this right now as some alpha n over mass dimension wise. It turns out that this is m chi 2 plus 3 n minus 2. Okay, and maybe just to show you how I know, or how you can figure out what are the right mass dimensions for a given interaction, we can again use this detailed balance trick. So let's look at detailed balance. Detailed balance is going to tell us that our forward process, the rate for our forward process, should be the same as our backward process, okay, when we're in equilibrium. And so let's look what that tells us. So the forward process, in my Boltzmann equation, I'll have the equilibrium number density n times, because n particles are meeting, times this, this weird n to 2 cross-section, which is something weird that we're trying to figure out how it should scale, minus an equilibrium, and equilibrium of just 2 particles that need to meet each other, and then it's just a sigma v of the 2 to n process. So that's my inverse process where just 2 guys are meeting and n are coming out. Okay, and this has to equal 0. Okay, and so let's just select out over here this weird object, the n to 2 cross-section that we're trying to understand its scaling, and what you see is that this equals to, what I have here is n equilibrium, and the power that it comes out to be is 2 minus n times this ordinary sigma v of 2 to n. And the reason this is important is because this cross-section, this is just a 2 to something class. This is an ordinary cross-section. It has mass dimensions minus 2. Okay? And the mass dimensions of this are 3 from the number density to the power of 2 minus n. Okay, so this is mass dimensions of 3 to the power of 2 minus n. And then you just plug this whole thing in, and if I'm looking at dimensions, it says dimensions of m to the minus 2 plus 3 and minus 2. Okay, and that's the dimensions that we fed up over here into the cross-section. Okay? So that's, again, that's one way to figure it out. Of course, another way would be to just think about how many particles I need to collide with in my rate, as we're about to write down, and figure out from that the dimensions like we did before. So this is one of a couple of ways you can figure out a dimensionality. And so let's look at the freezeout condition. Okay, so here's our freezeout condition. If I'm a dark matter particle, so okay, what I need is for my n to 2 rate to equal Hubble. And let's write out what is the n to 2 rate. So if I'm a dark matter particle, I have to have now n minus 1 other guys come and collide with me, right? So I need to have here n chi, so the rate for the n to 2 goes like n chi to the power of n minus 1, okay? Times the strength of the interaction, which is the sigma v n to 2 that we just wrote down, and I have to require that this is of order Hubble. Now, we use the exact same trick of n chi at freezeout, which we redshifted into T equality. And what's important is that every factor of n chi of the dark matter number density has 1 power of T equality in it. Okay, and so if you go through the math, it's identical to what we just did for the 3 to 2. So I'm just going to give you the bottom line. The bottom line is that you find that m chi goes like this self-coupling times T equality to the power of n minus 1 times m Planck to the 1 over n power. Okay, and so this is sort of the general n to 2 case for these self-annihilations. So it's really a generalized geometric mean. And in particular, if you were a fermion or there was a Z2 symmetry, and sort of the lowest order next thing after 3 to 2 that you could do would be for 4 to 2. So if we take, for instance, n equals 4 and we look at 4 to 2 processes, what you find is that m chi goes like alpha, and it turns out to be around 100 keV. Okay. Okay. So this is what I wanted to show you about Simps, the 3 to 2 piece, and also in general for the n to 2. Before moving on to the fact that I've been cheating you, I just want to draw you a toy model, because it might be, for 2 to 2, I think it's very easy to understand. We're all familiar with 2 to 2 annihilation cross-sections, but you might think that it's a little weird to start thinking about 3 to 2 interactions or higher point interactions, and I just want to give you a very easy toy model just to show you that indeed you can write this down. And in our lesson tomorrow, we're going to be writing down more complicated theories that admit this behavior as well. But let's just write out quickly a 3 to 2 toy model. So 3 to 2 toy model. And a very easy one that we can do is just to think of a single scalar with a z. Just to think of a, sorry, let me write this down differently. So this is a toy. I'm going to call it a Z3 symmetry model. Okay, so it's a single scalar with a Z3 symmetry. And what that means is that I can write down in my Lagrangian terms that go, as chi cubed, because that's invariant under a Z3. And I can also write down 4-point interactions, like absolute value of chi to the 4th. Okay, so I have now vertices in my theory that are either with 3 legs coming out or 4 legs coming out. And so there are 2 types of contributions that I could write down for to get a 3 to 2 process. So first, let me glue together 3 3-point interactions. Okay, so here's one 3-point interaction. Here's another 3-point interaction. Okay, so here's 3-point, whoop, here's another 3 points. Okay, so these are, this is where I use 3 3-point interactions, 3 3-point interactions. Okay, so that's one option, and this is the option that inspired the fact that we parameterized our cross-section as, alpha cubed. Okay, the fact that we took this alpha cubed over mass to the 5th. Sorry, this is for the 3 to 2, not in general. Okay, so this is one example of how you, just from this simple toy model, can get 3 to 2 annihilations. And of course, I can also take one 4-point and glue it on with one 3-point. So let me show you how that looks like. So I can also do, for instance, I can take, here's a 4-point interaction and glue it on to a 3-point interaction. Okay. So this is 3 3-points, and this is a 4-point plus a 3-point interaction. So just to show you that it's very easy to write down processes of this sort. Okay, even in a very simple toy model with a single scalar. Okay, so we've understood 3 to 2 interactions. We've understood that I could have a general n to 2 interactions. And now let's touch upon the point that was mentioned earlier, which is the fact that I have been, as I said, I have been cheating you.
Yoni, one question. In your second diagram, there are only 2 vertices. So in that case, it would be only alpha square, not alpha cube. So how do you deal with that? So in general, and this is true throughout, what we do at the mechanism level is I'm going to parameterize. I want to be able to encompass, in general, what happens across all
all theories, okay, that this is the process that controls it. What's important, so I parameterize it in a certain way. The coupling that we found over here, this alpha effective, that's why I called it alpha effective. It's not necessarily, in your theory, going to translate into a particular coupling. It might be an order 1 times a coupling. It might be some combination of coupling. What you would do in a given theory is you would write out, and we're going to do an example of that tomorrow, is you would write out in the theory, in terms of the parameters of your Lagrangian, you would compute what is the thermally average cross-section, okay? And then you'll require that this thermally average cross-section equals the amount that we've derived that it needs to equal. So this might give you, in your theory, slightly different mass because your coupling is different, or slightly different coupling. This is just a way to parameterize our ignorance. But in any given theory, you're going to break it down and sort of write your alpha effect. So you're going to call then, in this theory, you would call, let's say this was some, let's do an example. Okay, let's say this was some coupling kappa, and this was some coupling lambda. Okay, so you would have here, just in terms of the scaling with parameters, okay, you'd have some kappa times lambda, and in your cross-section it would be squared, and there'd be some mass dimensions, or there'd be a whole function over here, and you would just translate this equals alpha effective cubed over m chi to the 5th. And so you'd be able, and we know what the size of this is. This is what we've just derived. Whoops, sorry. We've derived what is the size of this alpha effective cubed over mass to the 5th. And you would just translate that into what does this really tell me in my theory, and over here you have some function of all sorts of m's and maybe other particles and other numbers. You would just translate this into, okay, what does this tell me in my theory about kappa and lambda? Is that clear? Does that make sense?
Yeah, perfectly.
Okay, great.
Thank you.
Okay, so now let's talk about what we haven't, what's been hidden sort of behind the rug over here, and make sure that it's a consistent picture. So how have I been cheating? And I'll do this in like a quote unquote, okay? When we solved our Boltzmann equation, or when we did our freezeout condition for these 3-to-2 annihilations, and likewise for this n-to-2, we've implicitly assumed that I had one temperature that governed the entire system, right? I didn't write down, this is the temperature of the standard model, this is the temperature of the dark particle. We assumed that I had one temperature that could describe the whole system. So this is what we've implicitly assumed, that there's one temperature, one temperature for the entire system. Now, the reason that I say that this might be something you'd worry about is that if we think about these 3-to-2 interactions, then what they're doing is actually pumping heat, right? So if I take, so this pumps heat, right? If I have 3 particles that are coming out, then 3 particles are coming in. The 2 that are shooting out are each more energetic than the outgoing ones, right? So these ones are coming in cold, and these ones are coming out hot, okay? And so if this was really all that was happening, then there's issues with structure formation. This is something that would lead you to very light, very hot dark matter, and this is not what we want to be doing. So there has to be some way for everything that we've described so far to be okay. There has to be some way to shed this heat that's being pumped into the system. Okay, so we need to shed heat. Or another way of saying this, we have to be able to cool. Or we have to be able to dump entropy. Okay, and you can dump entropy either to some other light state in your dark sector, some light particle, or to the standard model itself. We just have to be able to dump that entropy. Okay, so this can be to some other light state, or to the standard model. Sorry, not of, or. Okay, so let's look at, for instance, the easiest way you would think of how to exchange heat with the standard model. Okay, so here's my cooling process that I want to have happening. I want to have chi's scattering off, oops, here are my chi's, and I want them to scatter off of standard model particles. Okay. Okay, so this would be a process that would be cooling the dark matter, right? Time is going this way. Okay. And I want this process to be active while 3-to-2 freeze-out is happening. Okay. So we want this to be active want to be active while 3 to 2 is freezing out. Okay, because we want that entropy to be dumped. We want to be able to cool. But if this process is active, then you could ask, well, let me take the same diagram and just flip it on its side, and then we just get the regular 2 to 2 annihilation diagram, right? So then I could just flip it on its side, and I get just an ordinary 2 chi's annihilating into 2 standard model particles. And I definitely don't want this to be important during freeze-out, because if it is, then we're not a simp, we're back to the case of the WIMP, right? So, so this is the question. So I want to be able to cool, but not annihilate. Okay, so we want to cool but not annihilate at freeze-out, but not annihilate. And up here you might be worried because these cross-sections, right, these seem very similar types of diagrams. You'd expect that there isn't some big suppression that's happening from the cross-sections. But the key is that what we care about are rates, not just cross-sections. Okay, so let's write out what are the rates for these two different processes. So here we are. Let's look at this kinetic term, this kinetic coupling term, or elastic scattering term. So the rate for this equilibration process for us to cool, so it has a piece that cares about some 2 to 2 cross-section, okay, some 2 to 2 annihilation cross-section. But in this case, if I'm a dark matter particle, here I am, I need to meet a standard model particle in order for this process to happen. So my rate is proportional to a number density of a standard model particle. And let's look at my annihilation case down here. Then I'm still proportional to some 2 to 2 scattering cross-section, annihilation, some 2 to 2 cross-section that I expect not to be very different from the previous cooling mechanism. But now if I'm a dark matter particle, importantly, I have to meet with a dark matter particle. So my rate is proportional to n chi. Okay, so what you see over here is that what's really important, what matters is who you need to meet. Okay, what matters in this case is who you need to meet. Okay, n chi versus n standard model. And so let's just take a closer look at this and see, indeed, can it be done? Can we cool without annihilating? So can it be done? And the answer is yes. So let's take a closer look. So let's write out the ratio of the annihilation rate to this kinetic rate. Okay? So the cross-sections are roughly going to cancel out between the two. And so what I'm left with is a ratio between n chi and n standard model. Okay? And so if we scatter off of light, abundant, relativistic degrees of freedom in the standard model, okay, so if we scatter, let's write that down. So if we're going to scatter off of light standard model species, okay, so these are things that are things that are relativistic. It could be, I don't know, electrons or neutrinos or photons, okay, at whatever time we're talking about freeze out. Then the number density of the standard model is unsuppressed. These particles are abundant. The number density of dark matter, which is freezing out not when it's non-relativistic, is exponentially suppressed. And so the ratio of these two number densities just goes like e to the minus m chi over t. Okay, this is of order, this is of order 10 to the minus, we said m over t is x freeze out. It's roughly of order 20. This is of order 10 to the minus 8. Okay, so this is much, much smaller than 1. And so we can naturally suppress the annihilation rate while keeping the elastic scattering active. Okay? So we want to scatter, that's the key, we want to scatter off of these light standard model species. Okay? And then we can cool without annihilating, and the story that we've told is an appropriate story. Okay? And importantly, as I alluded to also yesterday when we described the WIMP, this is something that happens also for the WIMP. Okay? So it's known. And what we see over here is that this the kinetic equilibrium process is really decoupling later than this 2 to 2 annihilation. Okay, so it's also known for the WIMP that you can shut off your number changing processes while still maintaining the thermal equilibrium processes active. And this is exactly this ratio between annihilation and elastic scattering. So let's write down these conditions in another way and just sort of see what we're finding. So here are our conditions. At freeze-out, we want the kinetic rate compared to the 3:2 rate to be, so at t equals t freeze-out, we want this ratio to be larger than 1. We want the cooling mechanism to be operational at freeze-out. And at the same time, we want the annihilation rate compared to the 3:2 rate at the time of t freeze-out to be smaller than 1, because we want the annihilations to be shut off, so that the 3:2 process is the one that's important for the number changing process of dark matter. And so let's just parameterize. Again, let's parameterize this, our interactions. So let's parameterize our Simp with standard model interactions. So let me think of it as if here's my dark matter, okay, and here's my standard model. And what we said is that we have to have some way to cool, so we have some little interaction here. Let me call that the strength of that interaction epsilon. Okay, epsilon is going to be small, that's why I'm choosing it as epsilon. So let's call this sigma v for our kinetic process, which is of order sigma v for the annihilation process. Let me define this all as some epsilon squared over m chi squared. Okay, again, just a parameterization that's true in general. And in any given model, I can relate what my model parameters, how they map onto this epsilon. And then what we find from these conditions is there's some range of epsilon where everything works. Okay, so you find there's some epsilon min, some minimal value for epsilon. It goes like alpha effective to the square half, t equality over m Planck to the third power, to the 1/3 power. And there's also some maximal value that epsilon should not exceed for this to work. And that goes like alpha effective to the t equality over m Planck to the 1/6 power. Okay? And so roughly speaking, if I want to think of sort of at this plane of mass of dark matter versus epsilon, then there are some two curves here, epsilon min and epsilon max, okay? Epsilon min, epsilon max. And as long as I'm between these curves, the mechanism is working, and I have Simp dark matter. Okay, and to give you a sense of what these numbers are, so maybe this is just to make the point, if I'm beneath epsilon min, then there's no kinetic equilibrium. Okay, I haven't been able to shed the heat, and that's no good. If I'm above epsilon max, this curve is where we sort of go to that, the 2-to-2 annihilations take over, and we have a WIMP-like dark matter particle. But in between, the conditions are met, and we have Simps. As I said, just to give you a ballpark for what these numbers look like. So for instance, if I look here, let's say between MeV and 100 MeV for the dark matter masses, then over here, these are epsilons that are between 10 to the minus 11. I think up here, oops, it's like 10 to the minus 5. This is maybe sort of 10 to the minus 9. Okay, so these are very small couplings to the standard model, and definitely a broad range of parameters in which everything works. And importantly, as long as we're in this regime in the middle, as long as the conditions are met, the result is insensitive to what particular value of this coupling we had.
You need one question to understand the scenario. So before you said that in the Simp, the coupling is strong interacting, so it's a strong coupling, and the WIMP is associated to the fact that the coupling is weak interacting, no? But in this epsilon, somehow is representing the coupling, but it seems here that the WIMP-like particles are having a larger coupling with respect to the Simp.
So there's, so that's a great point. So I want to emphasize the difference. There are different couplings, okay? The Simp is controlled by a self-interaction. That's what we called the alpha effective, okay? That is a strong coupling. And again, it doesn't have to be strong. It could be light. If I take it to be light, smaller than order 1, I just get lighter, I get lighter masses. As you see from over here, again, if I go back to the fact that I've sort of been alluding to the fact that we're going to have some constraints on how low we can go in mass if we want to be in thermal equilibrium because of existing constraints, for instance, from BBN, and we're going to be, I hope we'll get to talking about those tomorrow, then, I can't take that self-coupling to be too small because I'm going to run into problems with BBN, for instance, okay? but that is a self-coupling of the dark matter to itself. Now, unlike the WIMP, in the WIMP I only had one coupling, right? I just had this one coupling that was there, and some of the other processes I might have had more couplings, but in the WIMP there was one coupling. Over here in the Simp, you see I actually have two knobs. I have two different couplings. I have my strong self-interactions of the dark matter that are setting the relic abundance, and I have some very, very weak interactions with standard model or other light particles that ensure that I can shed the heat that's being pumped into the system. So these are two separate, for the Simp case, I have two separate couplings, two separate types of interactions that need to be happening. Okay?
Okay, that is clear.
Okay.
Thank you.
Okay, and also importantly, I mean, you can see over here, you see this curve that I drew, the top curve, our epsilon max curve over here, I wrote down in blue that it's WIMP-like. This is just showing you sort of, this is indeed that weak-like, that WIMP-like curve, and you see over here that for the WIMP, I can take the couplings to be, I can take the coupling to be substantially smaller than 10 to the minus 2. I can just continue taking them smaller and smaller and smaller, and I'm led to smaller and smaller masses. If I was living on this epsilon max curve, then it would be just an ordinary 2 to 2 annihilation, something that we learned about yesterday. Okay. But if I'm smaller, if my coupling is smaller than that, then my strong self interactions are going to take over, and then we're a Simp.
Perfect. Thank you.
Okay, great. So the next topic that that I wanted to discuss today is going to be cannibalism. Okay, cannibalism is what happens if we weren't able to shed this heat. Okay, that's our next topic. So let's talk about cannibals. Cannibalism. And this is an idea that was originally proposed in a paper by Carlson, Machakek, and Hall in 1992. Okay, and it's deeply related to Simps. So let's look back at our 3 to 2 process. Okay. And ask what would happen if we weren't able to shed that heat. Okay, what would happen if we didn't have these interactions with some light abundant particles? What if didn't dump that entropy into these light abundant species? Okay. And so this is sort of in the situation that we're going to describe here. It can happen in general if you just have 3 to 2 interactions without any additional particles, additional abundant particles to interact with. And it can also just be in general for a dark sector that has a mass gap. Okay, but I'm going to be describing it from this 3 to 2 perspective. Okay, so if there's no way for us to dump our entropy, then there's no reason that my temperature, when we did our freeze-out condition, etc., there's no reason that the temperatures of the dark sector and of the standard model should have been the same. There's no reason that I should be thinking of just one temperature that's identical to the standard model. So there's no reason to have same temperature as the standard model. Okay, so let's consider what happens when dark matter becomes non-relativistic. Okay, so when dark matter becomes non-relativistic, when the temperature of dark matter, and now I'll make sure to keep an index that's telling me that this is the dark matter temperature, because it's no longer identical to sort of the temperature of the standard model bath. So when the temperature of dark matter drops beneath its mass, then 3 to 2 is converting the mass of one chi into kinetic energy of those final state products. So it's converting it into kinetic energy of the others. Okay, and that means that those two chis, those two dark matter particles that are coming out at the final state, they are now relativistic, okay? And then they're going to quickly scatter off of themselves to distribute that kinetic energy. So let's just write this out. So these guys, the resulting chi's are now relativistic, and they're going to quickly scatter off of other chi particles. Okay, so I have some, some self-scattering chi that goes to chi that's going to happen, and this is going to distribute the kinetic energy back into this bath of chi particles. Okay, and so what this does is it's heating up the bath. Okay, I've just described to you sort of in general how it's heating up the bath, heating up the bath, and in particular, of course, raises temperature of chi. Okay, so this is what's called, this is why it's called cannibalization. Okay, cannibalization. Okay, and the term that that Lawrence Holland Company had the reason that they had used this name already back in 1992 is you can kind of think of it like these chi's eat themselves to stay warm. Okay, so this is a cannibal process. So let's just work out what is actually happening here to the temperature to understand and to understand the relic abundance in this case. So how much do they heat up? Okay, so right, I'm assuming that the chi's don't have other particles that they can talk to, so they're only scattering amongst themselves. And if they're only scattering amongst themselves, that means that their co-moving entropy is conserved. Okay, so their co-moving entropy is conserved. So the entropy of chi times a cubed is a constant. Okay. Now the entropy of chi is rho of chi, the energy density plus pressure, which is going to be negligible here. Oops, divided by the mass, because these are non-relativistic guys. Oops, just did that again, divided by the temperature. Okay, great. Divided by the temperature of these particles. And these things are non-relativistic, so I can drop the pressure, and what I have is rho chi over T chi. Now, these are non-relativistic, so the energy density is just mass times number density, m chi times n chi. I'm not changing the denominator. And now let's plug in the fact that these number densities are non-relativistic. Okay, so let's just plug in, remember we're going to have this temperatures and masses, but we're going to have an exponent. That's what's important. So this is going to look like m chi over t chi, some factors here, m chi, t chi over 2 pi to the 3/2 power, and importantly e to the minus m chi over t chi. Okay? And so, and since we know that this scales like 1 over a cubed, the conservation of entropy is going to tell us, so conservation of entropy implies the following. What we get is that T of the dark sector scales like 1 over the logarithm of the scale factor. And I remind you, so I can also write this as, oops, just write it in the following way. This goes like 1 over logarithm of 1 over T, and that's because T, so this is T, this is the T of photons, okay? This is T photon. And that's because the scale factor goes inversely with the temperature of the photon bath. Okay? So, if I'm comparing, okay, so this is the result that we find here. So you see what's happening is that the temperature of the dark matter is growing exponentially compared to the temperature of the standard model bath. Okay? The temperature of chi is growing exponentially compared to the standard model bath. So this is what's happening in a cannibal sector. Temperatures are not the same, and they're not just different by an order 1. There's an exponential growth of the dark temperature compared to the standard model. And the last thing that I want us to do today is to also see what is the abundance that we would get for this. So we can also estimate the abundance from this, okay? So our abundance is, we have m chi times n chi today. So I have a 0 up there. Let's start with this, divided by S by the entropy today. So let's just write this in the following way. That's m chi. And now number densities and entropy, they redshift. This. I'll redshift from today to freeze out. Okay, so let me write this as n chi at freeze out over S at freeze out. Okay, and now again I have this is non-relativistic, so I can just write this in another way as T as the temperature of the dark sector at freeze out times the entropy of the dark sector at freeze out divided by the entropy of the standard model at freeze out. And now what I do is I take this and I plug it in to get our omega. So here's omega dark matter. And I remind you that omega dark matter is m chi times n chi today over critical density. Okay, and so let's just use what we've just written in the previous line. So I'm just going to multiply by S naught on top and bring it over. So what we get over here is m chi. I have n chi at freeze out divided by rho kriti S naught over S freeze out, and then I write this as temperature of chi at freeze out, S chi at freeze out, S naught over critical density S at freeze out. Okay, and when you plug in all of this, here's the bottom line that we arrive at. So this equals 0.6. I'm taking into account all the order 1s. M chi over EV divided by X of chi at freeze out. So that's M over the dark temperature. S chi F over S of F. Okay. So this is the result that we arrive at over here. Okay. And so you see that you end up with very light dark matter, let's say of order the EV scale, unless somehow this ratio of entropies is very large. Okay. Unless there's either a huge temperature difference or some huge number of degrees of freedom difference. So this gives you very light dark matter. And what you're going to see related to this in our tutorial on Thursday is that this result relates to something that's called the elastically decoupling relic, or in short, ELDER. Okay, so you're gonna see this the ELDER solution, I hope, in the TA session on Thursday. And this is something, if you want to read also more about it even beforehand, this is a paper by Kuflik and Perelstein, Ray Lawyer, and Tsai. And it's a PRL from a few years back, 1512.04545. And what's happening in ELDER is the following. So in Simp, let me just and I'll finish with this. So here's our Simp process, right? 3 chi's go to 2 chi's, okay? And we said we also had a process that we needed to have active, which was our thermalization process, okay? So I needed to have some scattering of chi's off of some other light species. Let me call it phi over here, okay? And for the case of a Simp, which is what we derived. So if I was looking at the case of a Simp, what needed to happen is that this first process, this decoupled first, and only later did this elastic scattering decouple, right? This is the elastic scattering decoupled second, by which I mean that it was active during freeze out, right? That was our condition so that I wouldn't be cannibalizing myself. What you find in the elastically decoupling relic, an elder, is that the order of which process decouples when is exactly reversed. Okay, so for the elder, the elastic scattering cross-section process is the one that decouples first, and these 3 to 2 decouple second. And when this is the case, as you're going to be deriving in the tutorial, what you find is that something very curious, the relic abundance of dark matter now has an exponential sensitivity to the elastic scattering cross-section. Okay, so this is going to go like e to the minus, ballpark this sigma v elastic. Okay, and so in this case, the dark matter density, the dark matter abundance that we observe today is determined by this elastic scattering process, which is a process that doesn't even change the number of dark matter particles in the universe. Okay. And finally, just to sort of to finish off this, so this is, let me just write this out. This is going to be in our TA session. Okay, so you guys are going to look at this in more detail, I hope, on Thursday. And what I just want to end with is just showing you that something that's true in general for all of these different mechanisms. What we see, but in particular for this WIMP and SIMP and ELDER, is that if I just think of sort of the relative size, let me draw this down here, okay? The relative size of these two types of processes that we've been talking about today. So I have some dark matter standard model interactions. Okay, these are these 2 to 2 interactions compared to the 3 to 2 self interactions. Then what you find is that depending on the relative size of these processes or of these couplings, you're in a regime where you realize one mechanism or a different mechanism. Okay, so for a certain size of these, certain relative size, there's some regime where I'm WIMP-like, and then we flow to a regime where we're SIMP-like, and then we actually go to a regime where we're an ELDER. So this region over here is where we're a WIMP, this region is where we're a SIMP, and this is the region where we're an ELDER. Okay, so that means that in these different regions, if I'm a WIMP, then what's controlling is chi to phi, regular annihilations that we're familiar with from yesterday. If I'm a SIMP, what's important here are these 3 to 2 interactions. And if I'm an ELDER, then oddly enough, what's controlling things is actually an elastically scattering cross-section.
Is there a way to overimpose the mass dependence for the three different mechanisms?
So what do you mean by overimpose?
I mean, for the WIMP, we saw that there is a ranges of values for the masses, and for the SIMP, we saw that there is also a very similar range of masses. For the ELDER, is the same. I mean, it can have a large range of masses, or it is more specific?
It can have a large range of masses. What you see is that it's very sensitive to the size of the cross-section. So, and cross-section is a combination of coupling and mass. But looking back to, let me think for a second if we have. So yeah, let me scroll back for a second to that plot that we drew of the epsilon min and epsilon max. Okay, let's take a look at this plot that we drew for the case of a SIMP, right? And I showed you that on that top curve, the epsilon max curve, that's where I'm a WIMP, right? I'm a weakly coupled WIMP, but I'm like at that standard 2 to 2 annihilations. This epsilon mean curve is exactly the curve of thermalization, okay? And basically, what it tells you is that if I was living exactly on this curve, that's where I'm an ELDER. And so you see over here, there's a range of masses and a range of coupling that corresponds to it. Okay, so there's a particular size for this elastic scattering cross-section such that everything works. And it's exactly basically sitting on this epsilon min curve. Up to certain, if you work through the order 1 corrections, of course, it shifts a little bit because we didn't really compute over here the energy transfer rate. We did something that was a little more hand waving-y, but conceptually, it's basically exactly this. Okay, so yeah, so the takeaway from here, and this is true by the way for all of the different processes that different mechanisms that we've been working through together, and that you might encounter as you study or as you work. Once you go down and write down a particular theory, you have some particle content, you have interactions, and what you have to do is go ahead and write down all of the types of processes that can happen. Okay, and very often you're going to find that you have multiple of these types of processes that are occurring, And then depending on which one is more important, which one is stronger in different regions of parameter space, you're going to find that you're realizing a different type of mechanisms. So it's very natural in all of these theories that when you write down a model, you're going to end up with some phase diagram for that model. So this thing over here is what I would call a phase diagram. Okay, which shows you over here, I fix a dark matter mass, and in a theory that has these two types of interactions, depending on the relative size between them, I'll be living in a regime where a different mechanism is setting the abundance that points me to a different type of interaction, a different type of strength, and importantly, different types of signatures that and constraints that you'd be interested in.
Okay, last question. So the kinetic diagram for the elder mainly depends on the dark matter standard matter interactions. While the self-interacting diagram for the simp mainly depends on the 3-to-1 coupling, so the self-interacting coupling. So how can it be that the elder correspond to this region of the parameter space, while the first that the couples is the weak interacting diagram? So if you go a little bit higher, when you compare the simp and the elder, it says that the first that the couples in the case of the simp is the strong interactive coupling, while it is the other way around for the elder.
Right.
And this is what is that explains indeed the phase diagram that is down there.
Yes, it does. And as you also see in the TA session, what it means is that I'm going to have, this result that we just derived for what's the relic abundance in a cannibalizing sector. You're going to see how this feeds into, I can then redshift to time from freezeout, I can go to decoupling, and I can sort of shift through to understand through the cannibal result that we got, why we get this result for elder. And indeed, what that means is that at the time of decoupling, the time of this kinetic decoupling, okay, which is when this process over here shuts off, I'm having a cannibal. I have a sector whose temperature is going through this evolution, and so that's why I need this process to be active. Yeah, and you can. So if you want to read about that, there's definitely. So this diagram, this phase diagram, is a phase diagram that you can find also in more details about it if you want to read in the original elder paper. So there's a lot of So this, if you work through the case of elder, this is the phase diagram. This is the phase diagram that you get.
I see.
And you see what's important over here is that you see how do I know that, let's say, this flat curve is the simp? Well, it tells me that if I'm between some epsilon min and epsilon max, if I'm between some two values of the 2-to-2 interactions with ordinary matter, then I'm insensitive. My result is insensitive to the size of that epsilon, and that's why it's flat it's horizontal over here. Okay, it's just determined by this coupling of the 3-to-2. Whereas for the elder, you see that for the elder, once I have a strong enough interaction of 3-to-2, I don't care about the particular details. All I care about is that I'm cannibalizing, and that's why it's vertical, and the relic abundance is set by a particular size of the 2-to-2 interactions. So the story is consistent.
I see. Very well. So is there any other question for unit? So it seems that there are no other questions. I think that we can stop here for today. So let's reconvene tomorrow morning at 10. Thanks a lot, Yonit, for this lecture, and see you tomorrow.
Thanks so much, everyone. Take care.
Bye. Thank you.